Let's get started with Notebook 4. Madeline, you're up.
All right. Can folks see the slides on my screen?
Yeah.
Awesome. Okay. So most likely, everyone's experienced this Doppler effect that's here in the picture. Have you ever heard an ambulance go by, maybe a motorcycle, a car? You notice that as it approaches you, it starts to increase in frequency. And what does that mean? That means the sound gets higher in pitch. So that classic meow as a vehicle goes by you is actually the Doppler effect. We're going to talk about how that relates to stars. Now, I'd ask a little bit of patience with folks as we go through this notebook. I'm going to lean extra heavily on our mentors today in the chat. I'm a little bit sick. It means I'm not quite as sharp as I usually am. So if you ever find something in my explanations where you're like, that didn't quite make sense, please feel free to ask in the chat and I can answer it verbally, or our amazing mentors can answer in the chat. So returning to this Doppler effect, what happens is as the object is moving, the sound waves get compressed in front of it, and as those wavelengths get shorter, seen here on the right, shorter wavelengths, they get higher in pitch. And the same exact thing happens in light. So what does that look like when we're looking in astronomy context? Instead of an ambulance moving towards us and going meow, we are in fact getting stars moving away from us. And as they move away from us, the light coming from them gets stretched out as if it were on a string, and it becomes a longer wavelength. And the longer wavelength is redder light. If instead a star is moving towards us, just as we saw those sound waves bunching up at the very front of the ambulance, making it higher pitch, we're going to get shorter wavelengths of light as they bunch up, and that's going to give us bluer light. So longer wavelength redder, shorter wavelengths bluer light. So we can actually use this phenomenon called redshift in order to tell a couple of things about astronomical objects. The first type of redshift we think about is that movement. So stars moving away from or towards us, or in the case of this GIF on the left, a galaxy moving away from or towards us. There's also another type of redshift that occurs when space itself is expanding at every single point. And this is what is causing our universe to expand. This is not the best GIF ever because these two stars should be moving away from each other. But because of that relative motion, we're going to get redshift. And therefore, we can use redshift actually to tell how far away things are in the universe because they're moving faster the further away they are. And we won't talk quite about type 3 in this context. Okay, so what can we use this redshift for? We can use it, as I mentioned, to help measure how far away things are based on how fast they're going. Also to do things like determine the relative age of galaxies based on how far away they are. And to even find exoplanets as they pull on their star, causing them to wiggle back and forth. So what does this look like when we're talking about light and the kind of light we observe in astronomy? Well, on the top here, we have a rainbow. Now, the scientific term for a rainbow is a spectrum. And what we're seeing in this example is that there are certain lines, dark black lines. This is what's called an absorption spectrum. This means that of the full rainbow of light coming from, say, a star, every wavelength of light is being emitted from purple to red, but certain wavelengths are being absorbed. And those are very specific wavelengths. It's always going to be exactly the same wavelength. And we know what this looks like. So if we instead see a difference in the spectrum, if that absorption line, that dark black line here, is shifted from where it should be in wavelength space, we can tell one thing. We can tell that the object is probably moving, and we can tell, based on where that line is, this lambda meaning wavelength, of the rest frame, meaning the thing that's stationary, and the one that's moving, the lambda nu. We can use this difference in order to tell how fast this object, say a star or a galaxy, is moving. So this is actually what a spectrum looks like. Here is a beautiful rainbow depiction of a spectrum, but what it looks like in reality is something a little more like this. So as a function of wavelength, so that the length of the waves we saw depicted in those first diagrams, how much light you are getting on every one of those wavelengths is here on the y-axis. And note that, of course, it's not, exactly the same amount of light at every level, but we do see very clear absorption lines that I mentioned. So these are sort of constant, physical constants. Say, for example, there is hydrogen in your star. That hydrogen is going to absorb the light at a very specific wavelength every single time. Every single time it's going to be at this, 430 nanometers of wavelength. But what happens when we see a shift? Let's go back to this one. Let's look at this one because it's the one I've highlighted here. So this absorption line, if instead when we observe the spectrum, we see, oh, it's not where we expected at, 480 nanometers. It is in fact at 500 nanometers. That's not supposed to be the case. So what we can tell is that this star is moving. And we can use that information about the wavelength that it would be if we were standing right next to it, and the wavelength that we would see if it was moving towards or away from us, in order to um, tell the velocity here, this v value, um, and tell how fast our star is moving. So the velocity of the star in this particular formula, this exact form that I've given you here, we're going to say that if v, the velocity, is less than 0, the star is moving towards us. And if v is greater than 0, the star is moving away from us. And in this case, remember this number, c is the speed of light. That's a constant value. And that's going to be 3 times 10 to the 5 kilometers per second, or 300,000 kilometers per second. So I'm going to flip back to this so we can remember it, but write this formula down for now. We'll take a screenshot, and we're going to use this in order to get information about Andromeda and the stars in Andromeda. All right, are folks seeing my Jupyter notebook?
Yes, we can see fine.
Thank you. All right, so what can we do with this information about radial velocity? Well, before we start, as you learned yesterday, we always have to import these modules, NumPy and Matplotlib. So I'm going to just execute this cell. Okay, so now NumPy and Matplotlib are loaded up and ready to go. So let's scroll down. Okay, so what we're going to do today is we are going to find how fast, what the velocity is of certain specific stars. So, in the folder, I'm just going to show you, you don't need to do anything with this folder. I'm just going to show you where it lives. So in your SIP Python workshop, in this folder called data, are all of these text files. And what this looks like, it looks a little something like this. Now, this means nothing to me as a human being with eyes, but fortunately, we can do something with these data in order to understand what they are telling us. So, before we get to that, what we're going to do is, our goal is to find out the velocity. So we're going to create a function that can tell us what the wavelength change is going to be. Remember this, we have like a new lambda when it is moving at some velocity. So we're going to make a function that can calculate that for us. So here is an empty function. And we know that if it's moving, the new lambda and the rest lambda are not equal. So let's look again at that equation. Okay. So if I want to get out the new lambda as a function of the rest lambda, I'm going to put it in this form in my function. So our inputs are the rest lambda and the velocity, and we want to get out. Our return is the new lambda. So new lambda as a function of rest lambda is let's double check that. All right, so 1 plus v divided by c times the rest lambda. Awesome. Okay. Can someone make a prediction? Or everyone make a prediction. We don't need to post it in the chat. What's going to happen if I run this function right now? Remember that when you have a function, these are our inputs. So this has a defined value, this will have a defined value. Does everything in here have a defined value? The answer is no. Let's see what happens if we were to run this. I'm creating a new cell just to test this. I'm going to shift to moving, and I'm going to say the rest lambda is, I don't know, 500 nanometers, and the velocity is maybe 100 kilometers per second. Indeed, we get an error because we did not define c, the speed of light. So remember, you have to define everything that's in your function. So here I'm going to take c, and I'm going to say it's equal to, let's go back to what was our value? 300,000 kilometers per second. So there's a couple ways to write this. My favorite way, because I'm lazy, is to use scientific notation. So it's 3 and then the letter E and 5. That means 3 with 5 zeros after it. The other way to write this would be, of course, 300,000. But then I have to actually count out the zeros, and sometimes I make mistakes. Okay, so now if we were to run this, we would get a result. I'm going to delete that cell, and we're going to continue with our activity. Okay, so remember we noted that if the star was moving towards us, the velocity would be greater than 0. So let's test out what happens when we have a rest wavelength of 6,000 nanometers, and we're going to apply some positive velocity to it. So shift to moving. What I'm doing here is I'm pressing the tab button because once again, I'm lazy, and in coding, there's lots of awesome shortcuts you can use. And so when I press tab, it auto completes the function. And my rest lambda, and let's use the variable name, rest h alpha. So that has the value of 6,563 nanometers. And then we're going to choose some velocity. So in this comment here, it suggests we use maybe 200 kilometers per second. So pause here to make a prediction. Let's go back and remember this silly diagram again. If it's moving towards us, as it is in this case, what's happening with our wavelengths? Are they getting shorter or longer? Okay. Use that to make a prediction here. What's going to happen? Is my wavelength going to be less than or more than 6,563? Let's see what happens. Okay, it's longer. I'm gonna be entirely honest, guys. I think the head cold is getting to me. That doesn't actually make sense to me. And there's a mentor here who can hop in and tell us a little bit about why we're seeing that. Perhaps we've coded this with the wrong sign. Please let me know.
Yeah, let's see. Um, Philip, Aparajito, Lordrick, either of you want to jump in here?
It's
Line 8.
it's the direction of the line of sight velocity, right? So there's a
Mhm.
sign flip because in one case, really the question is, are you taking the velocity with respect like coming towards you or away from you, essentially? So I think it's flipped around from what you would expect. So what would be plus is minus. So I think you should put a minus in your formula, essentially.
Okay. Let's do that for the sake of this.
Yeah?
Many, many moons ago, I wrote this all to match these notebooks, and so there may have been a reason at the time that we had that plus. We may need to put it back. But for now, folks, let's switch this equation to be minus V over C, and we'll see if that gives us the results that we expect. Okay, so we're going to move on for now, and we may have to come back up here and put back in that positive sign. And these are the sorts of things that genuinely, as a research
Or,
astronomer,
sorry,
Mhm.
or you can just switch the sign in the argument in cell number 10. So negative 200 instead of 200. That also works.
Technically, the way Raja wrote this, it's supposed to be that, oh, negative velocity is moving towards us.
Yeah,
Yes,
yeah,
exactly.
So,
Sorry.
right.
exactly. So that's the comment right above that line of code.
Yep.
V,
Okay.
yeah.
All right, so then everything we thought does make sense. When it's moving towards us, it has a shorter wavelength. Um, and to return to the comment at hand, this is genuinely the kind of thing that as a research astronomer you have to think about. Sometimes different research groups across the world will use, a different assumption about which way means positive, which way means negative, what your units are, all sorts of things like that. And so these are the sorts of things, that's why we did this investigation. That's why I asked you to say, what does your result, what you predict your result would be based on what makes sense, and what is it actually? And since we had a mismatch there, we were able to sanity check ourselves instead of just trusting our answer. We were able to think about, does that actually make sense? And figure out that I, in fact, had the wrong assumption that negative velocity is coming towards us. Okay. So now what can we do with this information? We now have a function that returns the red shifted wavelength. So we're going to start applying this to actual stars. So if you read these comments here, you can see that we've been given a couple of names of stars. Now in astronomy, we don't oftentimes use easily parsable names like Sirius or Betelgeuse, like you might have heard. Oftentimes, since there's so many objects, we use long strings of numbers. And so let's use one of those long strings of numbers in place of the star name. So I'm going to choose the first one, 64761. And then what we're trying to do here is, Jamaica, did they go over the star types yesterday?
Sorry, say that again.
Did they go over the stellar types yesterday?
We didn't do the slides, but yes, they definitely were talked about the different kinds of stars. Yes.
So to remind everyone, a main sequence star is a star like our sun that's in sort of like the middle longest period of its lifetime. A red giant branch star is a super large star. It's very red at the end of its lifetime. And an asymptotic giant branch or AGB star is a star that's sort of transitioning between those. Or after those. I don't do stellar physics. Okay. So what we're doing here is we're relying on the fact that you can concatenate or add strings together using plus signs. We saw a couple of different ways to add together strings yesterday. So I'm relying on the fact that a string can always be added to a string. So if I were to, for example, to print out the science file variable, it would be an entire string that's a combination of these three strings. And so what this allows me to do is to easily change out this star name without having to go, cut things out of the middle of a string every single time. And so that's why we do it in this format. Then what we're doing is we're loading up that sort of, non-human readable. I can't get any information out of this text file of a bunch of strings of numbers. But what we're doing is we're loading this first column and this second column into variables. The first variable is lambda, so the wavelength, and the second variable is flux, so the amount of light that is coming from each of those wavelengths. And we're doing the same thing for the template file. And we use this modifier, unpack equals true, in order to get each of these columns into these variables. All right, so if we execute this file, we should now have a science lambda variable and a science flux variable that are arrays of these values here in these columns. So what we're doing in this column is we're going to see, can we make these two, the star we've chosen, 600, 471, and a main sequence spectrum match up? So before we even interrogate what this does, I'm just going to show us what our output is. I don't use Jupyter notebooks in here anymore. I thought I ran the matplotlib inline.
Yeah.
Okay.
Uh,
Okay, folks, this is pretty
Okay, there we
important.
go.
This often happens, I remember, in PyaR tutorials. So in this cell working in right now, there is not this final line here. It says plt.show you need to add that for a lot of versions of Jupyter. So if you are not getting a plot when you execute this cell, you need to add this plt.show line. Okay, so what we're doing here, as we can tell based on this output, is we are plotting up those values that are in the science lambda, so the wavelength as a function, or flux as a function of wavelength. So this is our x variable, this is our y variable, and we're plotting them up. We're setting the color of that line to be red. See here, it's in red. And we're giving it a name. This is really important because if we didn't label what these plots were, we wouldn't be able to get this legend, and we wouldn't be able to tell what we were looking at. And this is yet another place where it comes in handy that we defined a variable that's a string that's the name of the template and the name of the star. So notice how we don't have to go look up here and then copy it and put it back down here again. We just have to define it one time, and then it's going to follow us throughout the rest of this investigation. So, now to the science at hand. Does this look like it is a good match between the red and the black? It's not a trick question, it's a terrible match. I don't think this is a main sequence star. So, let's go back up. Let's see what we can do to fix that. Maybe it's not a main sequence, maybe it's an RGB or a red giant branch star. I execute this cell again, and now I'm loading up an RGB star instead of a main sequence star. And I'm going to plot this again, and okay, maybe that's a little bit closer, but I think we can do better. So let's go back again. We're going to try our last option, which is an AGB or asymptotic giant branch star. We're going to execute this cell, and okay, that looks a lot closer. So now the question is, so we have a good idea of what a star should look like of this type. What the spectrum should look like for a star of this type if we were standing right next to it and it wasn't moving at all. So now we're going to use that information, that template in black, and we're going to see how much we need to change the velocity by of our actual observed star, 647.61, in order to see probably how fast 647.61 is moving. So how can we do that? So what we're going to do, first of all, by eye, it's going to be challenging to do if we're just trying to like make these red line and this black line match up. So we're going to scroll down and we're going to note that it says, okay, zoom in. Zoom in on the region between 700 or 7,000 and 7,200 angstroms. So how I'm going to do that is I'm going to use ax.set underscore xlim. So that's setting the x limits of the graph. And we're going to do 7,000 and 7,200. So what this should do is it helps us zoom in to see a closer match. I don't actually like this one. I'm going to choose a different range. I'm going to zoom back out. I really like this one. I think this one's going to be an easy one to get to the 7,500. So I'm going to zoom in instead. I'm going to choose my bottom range, 7,500, and maybe, oops, and 7,800. Okay, this one's going to be a lot easier to match. Okay, so as we can see a slight offset here. So what should we do to our science star to see if we can move it over to see how fast it's going? Why? I'm just going to start plugging in some guesses. Let's guess we saw 200 kilometers per second last time. Let's put in 200 and see what happens. Okay. Did it get closer or further away from the black line?
A little further away, I think.
I think that got further. So let's try the opposite extreme. Let's make it negative. Let's pretend like it's moving towards us. Ooh, much closer. In fact, that might have been nearly right on the money. Let's see if we can get it a little closer by shifting it a little further to the right. And remember, what made it go to the right was making this number more negative. So let's make it more negative and see what happens. 250. That feels like it was maybe a little too far. So let's split the difference. Let's call it 225, and we're going to say that's good enough. Okay. So by eye, we've managed to shift this over. And so by a process of comparing these and sort of a process of elimination, we've determined that this star is probably moving at 225 kilometers per second towards us. So I invite all of you to, after this, or, as we're moving on, go through each of the stars, find their matching template star. That's the star that imagines it was perfectly still and what it would look like in the rest wavelength, and to figure out the velocity in this same way by choosing a prominent feature and trying different velocities until you get a good match. So now that we've done this, let's take a look not just at one star, but at all of the stars in the Andromeda Galaxy. So we're going to do the same thing we did earlier, loading up a text file of sort of unreadable columns of data. We're going to unpack it, and we're going to put each of the columns into these different variables. Now, we don't necessarily have time to get into what each of these mean, but in brief, these first four variables are kind of like our coordinates on the sky. These are going to be our X and Y positions on our plots. And then these are the different wavelength bands. Now, I know we didn't go over the slides for this, but what this is this is kind of like finding those absorption features in the spectra again. And we're going to use these two different flux values in order to compute what's called color. And color in astronomy is not just the color that you look at and see with your eyes. It's actually a quantifiable value. And we're going to do some math. We're going to subtract these in order to get that quantifiable value of color, which can tell us a little bit about the makeup of the stars in Andromeda. So, first things first, we need to do some conversions for units. We're converting these xi and eta values to all be in the same units. Just go ahead and execute that. And that means now that when we plot this, we're going to have the units of kiloparsecs on both the x and the y axis. We're giving these labels, very important. We're setting our limits so we can see what we want to see. Just trust that we've programmed these limits correctly. And we're going to make a scatter plot. Now, a scatter plot is a bunch of points rather than connected by lines like the spectra we saw above. And so what are we doing here with each of these values? Remember, C is color. So we're making our color I assume, color is equivalent, this is really important, to our velocity. So we're saying the color of each point should be how fast it is moving. As we loaded up here in our table, we loaded up a velocity variable. This sets the size of the points. This is just messing with how they look. And we are setting a color bar, which is going to tell us what these velocity colors, what number they correspond to. So we can look with our eyes and say, okay, yellow is this value, blue is this value. So now that we've predicted what we're going to see, let's go ahead and execute it. Oops, remember we have to put in that plot.show. Okay, so based on what we discussed would be in this scatter plot, each of these points is a star. These are our coordinates on the sky, and our velocity. We can look here and we can see, okay, dark blue, that's something more like negative 700 kilometers per second. And our light yellow up here is something like 100 kilometers per second. Now, I can't get that much information from just this. So let's see what else we could do to make this a little more nuanced. So we talked about how redshift and blue shift are our blue shift is moving towards us and red shift is moving away from us. And we said, okay, that this 700, or sorry, negative values, there's a negative 700 is moving towards us. So I'm going to do something. We're going to keep this. I'm going to copy it so that I still have it to go back to if I want to. I'm going to comment it out by putting hashtags or pound signs in front of it. And we're just going to mess with this copied version. So I'm going to change this. I'm going to change my color map to be what's that one called? I think jet is one of them. And so this is going off script. It's something I usually do when I teach this section because I think it really helps us answer the question at hand. And we're going to keep this negative 700. And for reasons I'll explain in a second, we're going to make this positive 700. So let's see what happens when we just change the color bar. Oh no, that jet's no longer jet. Does anyone remember what the red-blue one is called now?
This cool warm, I suppose. You can try
Okay,
that.
cool warm. So I'm changing the color map that we're using to cool warm. Perfect. Okay. So what I've done by setting our red to be moving away from us, so positive velocities, and our blue to be moving towards us, or negative velocities, is now just by looking with our eyes, we can better tell what is going on with the stars in this portion of Andromeda. We can more easily see that the blue, these stars down here, are moving towards us, and the red up at top are moving away from us. So based on this plot, what do you sort of think the average velocity of Andromeda relative to us is? That's a determination you can make for yourself. But as you can see, it definitely is a lot bluer than it is redder. So that can tell us that most likely Andromeda is moving towards us with something around, say, maybe this color of blue, something between negative 200 and negative 400 kilometers per second. It's moving towards us. All right. So we're going to do some more work with these data later, but for now, I'm going to pass it off to our next mentor who's going to take us through our next notebook.